Hello everyone and welcome to our video today where we are talking about Organic Chemistry Chapter 2, Isomers. So, there's only a few basic foundational things that we're going to go over in this chapter. So let's get started. So we have structural isomers, which are isomers that share a molecular formula, but they have different physical and chemical properties. Then you have stereoisomers, which are composed of the same atoms and they are connected in the same order, but they have a different 3D orientation. So when that happens, we get into conformational isomers and configurational isomers. But before we get there, we need to look at chiral centers. So a chiral center is the basis of a lot of things we're going to be doing. So a chiral center means that one carbon atom is connected to 4 different substituents. So 4 different groups are attached to a central carbon. And so 2n, where n is the number of chiral centers, equals the number of stereoisomers that this molecule can have. So as we go further down our board here, we have conformational isomers and configurational isomers, which is kind of like the next subgroup of stereoisomers. So we have conformational isomers that differ by rotation around just a single bond. Then we have configurational isomers, a subgroup of which there are enantiomers. So this took me a long time to understand, so hopefully this helps you. We have enantiomers that says they are non-superimposable mirror images. So let's use your hands for example. Okay, your hands. If you were to draw a line right here, they are non-superimposable because you cannot put them on top of each other, right? You cannot, even if you turn them, that's not the same thing, right? They're non-superimposable because you can't directly put them on top of each other, and they are mirror images. If I was to put a mirror right here, I would see that they are mirror images. So they're non-superimposable mirror images, and they also have opposite stereochemistry at every chiral center. So if we're going to look at this example up here, okay, we have D-glucose and L-glucose. Now, if we're looking at this, first let's look. Okay, they are mirror images of each other. Perfect. But now let's look to see if the stereochemistry is opposite at every chiral center. So let's take this one for example. Right, if we're going to label this in terms of priority, we would just give the O. We would give this up here, we would have the 2. And then this group down here would have a 3. So we would be going 1, 2, 3. We would be going this way. However, because the hydrogen is on the horizontal here, that means we would flip it. So technically, this would be an R configuration, okay? So this would be an R configuration. So again, just to reiterate this last part, we prioritize these groups, oxygen being first. Then we look at, okay, it's connected to a carbon, but this carbon is also connected to all of this, while this is only connected to another oxygen and hydrogen. So this carbon up here would get the second priority, and this group would get the third. So you draw from first to second to third this way. However, because hydrogen is coming forward, you need to switch the direction of this arrow. So you'd be going back that way. That's just how you get your R configuration for this molecule. Now, if we were looking at the same chiral center in this molecule, you would see that we're going to give the same priorities that we gave before. We need a different marker here. We would be giving the same priorities we did before. So this would be 1, this one would be 2, this would be 3, 1, 2, 3, going this way, right? Oh, but again, the hydrogen is coming forward. We would need it to go back. So we're going to switch our direction. And this one, is going to be S configuration. So it's going that way. So here are our 2 configurations for this chiral center. And if you did that with each one of these, you would see that each one is going to be opposite on both of these molecules. And because every single one has opposite stereochemistry at the chiral centers, that means that they are enantiomers. However, if they are not all the same, let's say you did this to both molecules and they differ at some but not all of the chiral centers, that means that this would be a diastereomer, okay? And the diastereomers are not mirror images of each other. And finally, the last thing we're going to cover in this topic is relative configuration versus absolute configuration. So the relative configuration is stereochemistry that uses that you need to compare it to another molecule. So this would use D and L. You see this a lot with carbohydrates and sugar molecules. So yes, this would be relative configuration is D and L. However, absolute configuration is based on priority, and this is where we take into account the R and the S. Okay? So when we get into carbohydrates, we could talk about why this is D and why this is L, but for now, we're just looking at the absolute configuration using R and S. And one final thing I forgot to mention earlier when we were talking about enantiomers, one term that you might see is racemic mixture, and that means that it has a 50-50 mix of two enantiomers. So that's just a word that I've definitely seen come up a lot and just wanted to mention. So if you have any questions, please put them below. If not, we'll see you in the next video.